Hello class. We're going to finish up this lecture on RSA cryptography. So let's review. In the previous lecture we talked about Bob wanting Alice to send him whatever her plain text message is raised to the 7th modulo 713. That means he wants her to send him the least positive residue of whatever this is, modulo 713. So Alice has to take her message, which is 211, and raise it to the 7th power modulo and find the least positive residue modulo 713. So the repeated squaring method means that she has to decompose the power according to its binary expansion, and she has to calculate, she has to do squarings log base 2 of e times, okay, e being the exponent that she's supposed to use. So she has to do log base 2 of e squarings, and each of these squarings has to be reduced modulo 713, and the amount of work that each one of these divisions takes is proportional to the log of this number n here. So this operation, since it's the number of operations is a constant multiple of the logs of the numbers involved, it doesn't take that long. Alright, so now when she needs to merge all of these numbers here, she has to multiply these two and reduce it at modulo 713, and then multiply the result times this one, modulo 713. So she again has to do about log base 2 of e multiplications here. Right. So anyway, she sends this number 583 to Bob, and she doesn't care if Eve can see this because she knows that Eve doesn't know the inverse of 7 modulo phi of 713, because she assumes that that Eve is not good enough to factor 713. Of course, 713 is not really too hard to factor, but we'll get back to that. So okay, so Bob receives the number 583. Okay, so Bob knows that phi of 713 is 660, and neither Eve nor Alice knows this fact, so he can find the inverse of 7 modulo 660. Okay, so we use the Euclidean algorithm. 660 is 7 times 94 plus 2, and 7 is 2 times 3 plus 1. So 1 is 7 minus 2 times 3, which is 7 minus the quantity 660 minus 7 times 94 times 3, which is 7 times 283 minus 660 times 3. So 283 is the inverse of 7 modulo 660. Okay. So Bob just needs to compute the least positive residue of 583 to the 283rd power modulo 713, right? Because 583 to the 283 is congruent to 211 to the 7th to the 283, which is congruent to 211 to the 660 times 3 plus 1, which is congruent to 211 mod 713. So if Bob can do this, he'll recover Alice's original message. All right. So let's have him do that. Now, I'm just going to put this here because it doesn't really help me to write it all out. So we need to do squarings a few times before we get all the way up to 283. So we first find out what 583 squared is, modulo 713, and then 583 to the 4th, 583 to the 8th, all the way down. And each one you get by squaring the one you had before and then dividing 713 into it. So we have to do log base 2 of 283 rounded down squarings, and each time we have to divide by 713. Okay. And then we take the 283 and write out the base 2 expansion of it, and then 583 to the 283 is the product of all these numbers that we got up there. Actually, yeah, it's the product of all of these numbers, which I can read from this list up here. And then, so there are about log base 2 of this number terms that I have to multiply together. And so I eventually get 211, which is Alice's original plain text message. Right? So the total amount of work done by Bob is a small multiple of the base 2 log of 283 and also the base 2 log of 713. So we can write the amount of work that Bob has to do as some constant times the log base 2 of 713. Right. Now, even if the number n, which was 713 in this case, is really big, the base 2 logarithm of n won't be very big. I mean, relatively speaking. So, what Bob has to do, it goes very quickly. However, what Eve would have to do in order to figure out 211 is Eve would have to either figure out phi of n, or Eve would have to figure out phi of n and then find the inverse modulo phi of n of e, lowercase e, and nobody knows any algorithm for finding phi of a number or factoring the number that where the number of operations is like constant times the base 2 log of the number. I think the best algorithms people have is where the number of operations is about the 4th root of the number, which, if the number is big, is much bigger than the base 2 log of the number. I should talk a little bit about doing these computations. Of course, if you do these on a 4-function calculator, you will get the right answer if you enter all the numbers correctly, but you'll probably make a mistake somewhere, and it's a little bit hard to figure out. So you can also go online and use Wolfram Alpha. And Wolfram Alpha will, you just type in like 501 squared mod 713, and it would spit out 25. And it's very useful for checking your work. Also, I would recommend that if you go on, that you would go on Wolfram Alpha. So that's wolframalpha.com, I think. Well, okay. And what is really fun to do on Wolfram Alpha is enter a very large integer and ask Wolfram Alpha to factor it, and it's pretty good. And you should probably just to see to get a feel for the numbers involved, see how big the number you enter has to be before Wolfram Alpha starts having problems factoring it. And actually, it's pretty good for pretty large numbers. So that might be a fun thing to do. And it'll show you how big these numbers have to be in order for this kind of encryption to be secure. Well, that's all I'm going to talk about today. And again, thanks to Professor Crossan for the AV equipment, and have a good spring break. Okay, here we go. Here we enter some number, and actually let's ask it to factor that. And it didn't have any trouble with this one. Okay, so let's go back and see if we can put in a bigger number and see if it's big enough for it to have a hard time. So, oops, I have a minus sign in there. Okay. Oh man, it got that one too. Well, okay, so let's see. Let's try one more. Let's try making it a little bit bigger. Oh, I got that one too. I don't know. Maybe we should not. Can we not?
We can get rid of
Get rid of this.
Yeah.
Okay.